Well, see, dear students, so far we have discussed different state, variables, P, V, N, and T, different types of processes, isochoric process, isobaric process, adiabatic process, and representation of those processes on the PV plot. And in future also we will do so many questions based on this. So repeatedly you will get this type of plot and all these processes one by one I will discuss in detail, right? Now the next conceptual portion is state function and path function, right? So we have two types of thermodynamic functions. One are state functions. So at the name itself manifests that state function are those physical functions or thermodynamic functions which depends on the initial and final state of the system. So state functions depends on the initial and final state of system. Initial and final state of system. And final state means final value of P, V, N, and T. And initial state means initial value of P, V, and T. P, V, and T, and P dash, V dash, and T, like that, or P dash, V dash, N dash, T dash, all four variables may change. So initial value of P, V, and T and final value of P, V, and T, if any function depends, then that is known as state function. This is one meaning. Another meaning is mathematical meaning, that state functions are exact differential. Exact differential. Exact differential. What is the meaning of this exact differential means, and they are represented with this delta, right? So this is the IUPAC convention. Although representation is a matter of convention, so you can write or you can left, but IUPAC recognize this delta as a state function. Means if any physical quantity is written with this delta, then that is a state function. It is clear, right? So this is the representation. So what is the meaning of exact differential? That suppose that a quantity is x written with this, so immediately you understood, okay, this is what state function. I don't know whether people are following this convention, IUPAC convention, or not, but I am referring this with the latest IUPAC convention, which is given in one of the book by written by some molecular approach of thermodynamics. And in that book, this convention is taken from the latest recommendation of IUPAC. So this delta, I don't bother whether you have written any path function with this delta, I don't know that. But I will avoid to write such things. So see, exact differential means if you integrate this function between two limits, 1 and 2, so this is equal to x2 minus x1, right? So this is the meaning of exact differential. So state functions are exact differential and they depends on the initial state, means initial value of PV and T, and final value of PV and T, and they are independent how this transformation, or how this initial final value of PV and T has been achieved. So it is independent of the history of the system. right? So state functions are independent of history of system, independent of the history of system, right? So in this way, I mean, you can express the state functions, right? Now see, the following functions are state functions, like temperature, pressure, volume change, right? Delta E or delta U. This is called internal energy, right? Delta H, this is called enthalpy, right? All these are state functions. These are the examples of state functions. Delta S, entropy change, internal energy change, enthalpy change, delta A, Helmholtz energy change, and delta G, Gibbs energy change, right? So these are the main thermodynamic functions about which we are I am going to discuss in this chapter, right? Internal energy change, enthalpy change, entropy change, Gibbs energy change, Helmholtz energy change. So these are the example of some state functions, right? Now see the path function. What are path function? Path functions, so if you see path function, so path function depends on the path followed by the process, right? Suppose that if you are moving from one initial state to other initial state, final state, by some from one path and from other path. So in both the cases, if your that property depends on the path, so if it is different, then you can say this is a path function. So path function, first point is depends on the path, depends on the path followed by process, right? Second, they are uh, inexact differential, right? How they are represented as per IUPAC system? As per IUPAC system, this delta is used to represent, right? So suppose that any function, any physical quantity x, which is a path function. So what is the meaning of inexact differential? Means 1 to 2 is equal to x. Means you cannot subtract from this limit minus this limit. This depends on the path followed by the process, right? And so you have only two, path functions, two or three path functions here in your syllabus, right? So one is uh, work. Not every work is path function, but what for you in chemistry, what is if any point of time in thermodynamics, if work is referred, so you have to consider PV work. Basically, we have different kinds of work, but here I am talking about P, pressure volume work, right? So pressure volume work, this is what path function, and this is represented like this delta W. This 1 to 2 is equal to W. One more way to define this, path functions. Suppose that this is state 1, right? This is state 1, and this is state 2, state 2. Suppose that we are moving from here to here. This is one path, and again we are moving from here to here. This is another path. So we have started from here and moved to here. Again we have started from here, means again we are moving to the original state. So this will constitute a cyclic process. So in a cyclic process, in a cyclic process, this is not equal to 0, right? But if you take any one of this state function, and if you take a cyclic process, suppose that this is delta H, so this is equal to 0. So this is one more, way to represent state functions and path functions. Means state function, if you start from some point and move through certain changes to get the another state, and again you restore the initial state. So the delta H means change in the state function becomes 0, right? But here this is not equal to 0. So work, this is a path function. It depends on the path followed by the process. Means you can very easily say that W reversible means reversible process, and if you take irreversible process, so in both the cases, reversible and irreversible process, work is not equal, although the states are same. Suppose that you have started from initial state, same initial state, and you are moving to the same final state, one by reversibly, other by irreversibly. Work is not what same, right? Because in both the cases, path is different. Okay, and since it is path dependent, so this work is different. Now, see. Another physical quantity is path function, that is heat, right? Heat represented by Q. So this delta Q 1 to 2 is equal to Q, and is not equal to 0, right? So this is the way of representation of what path and state functions, right? So you have one more you have, that is heat capacity. Heat capacity. This is also path dependent. Path dependent, right? So if we see, suppose that this is one state, this is another state, and this is another state. Suppose that we have P1, V1 and T1, 1 mole of gas, 1 mole hydrogen gas. We have taken here P1, V1, T1. And suppose that we are moving from here to here through a constant temperature path, means here T1, and pressure is P2, V2 and 1 mole hydrogen, right? So this is one state of our system, this is another state of our system, and temperature is constant, means this is an isothermal path. Isothermal path, right? So you can suppose that change in internal energy is delta E1, enthalpy change is here delta H1, Gibbs energy change is delta G1, and work involved in this case W1, and heat change involved in this process is delta Q1, right? So this is one state, state 1, and this is state 2. Now I am taking another path from here to here. This is, I am explaining you how to understand state function and path function. Suppose that this time volume is constant, V1, pressure is what, P2, and temperature is what, T2, and 1 mole of hydrogen gas, right? So volume is constant, initial volume V1 volume is constant, so this path is called isochoric path. Isochoric path. So tell me, from here to here, from this state to this state, these two states are different. So if these two states are different, means internal energy change is different. So here delta, suppose that E2, delta H also, because state is different, delta H2, delta G2, and work delta heat delta Q2, and work delta W2. Suppose that from this state to this state, this is the changes. Now I am taking another change from here to here. So if you see, P2 is constant, this time T2 to T1 and V1 to V2. So this is isobaric path. Isobaric. So this time this state and this state is different from this state. So here delta E3, delta E3, delta H3, delta G3, delta W3, and delta Q3. So as per the above concept, here we are moving from this state to this state directly, and here we are moving from this state to this state, same state, indirectly in two steps, right? So what will happen at any moment of time? You can write delta E1 is equal to delta E2 plus delta E3. And this is always true. This is always true, right? So if you are carrying out any transformation, any change in a thermodynamic system in one step or in more than one step, state functions are same, right? State functions are same. Means whether you are moving from this state to this state directly in one step or indirectly in two steps, the magnitude, the change in the internal energy is always equal, because it depends on the state, it not depends on the path, right? Similarly, you can write delta H1 is equal to delta H2 plus delta H3. This is enthalpy change. Similarly, you can write delta G1 is equal to delta G2 plus delta G3. But you cannot write delta W1 is equal to delta W2 plus delta W3. You cannot write this. And also you cannot write delta Q1, Q2, delta Q3. So this is the meaning of what? State and path function. So any thermodynamic change, either it will be completed in one step or it is completed in more than one step. If initial and final states are same, then your state functions are same, right? So similarly, if you are performing any chemical reaction, if you are observing any chemical reaction, and if you are observing any one of the thermodynamic function, state function regarding that chemical reaction, whether the reaction is completed in one step or more than one step, the state functions means energy, enthalpy, entropy, even also. What I have forgotten, this entropy, delta S1 here, right? Delta S2 here and delta S3 here. So we can write here delta S1 is equal to delta S2 plus delta S3. Equation 4 means any chemical reaction or any thermodynamic process, whether it can be done or chemical reaction can be proceeded, can be completed in one step or in more than one step, enthalpy change or entropy change or Gibbs energy change or internal energy change is always constant, because it depends on the initial and final state. It is independent of what? All the path followed by process. So hopefully all of you are clear regarding this, what is the meaning of path function and state function, what is the representation of this path function and state function, and mathematical definition as well. So this is all about state function, path function, and general definitions of different processes, right? Uh, Reversible, irreversible, isochoric, isobaric, and what is state, what is path, what is process, right? every notation, change in state, everything I have completed in general, right? Now let's start. What is the meaning of heat? What is the meaning of work, PV work? How many types of work we have? What is the meaning of internal energy and thermodynamics first law? Zeroth law we have already completed in gaseous state because this involves the thermal equilibrium. If two objects, I think I have explained this, temperature as a potential. So I'm not going to discuss here zeroth law, that I have already discussed, right? So now I will start from the first law of thermodynamics, heat, internal energy, and PV work, basically pressure volume work. Now, see, first I am taking this internal energy. This is very important for, thermodynamic function and simply called energy. So whenever you will find the term energy or internal energy, then you will think about internal energy and you have to use the concept developed for this internal energy, right? Some books follow this symbol E or U. So whatever I am more used to for E, so I'm using E for this thermodynamic function, internal energy. How it is defined? So every time whenever you are going to define any this type of thermodynamic function, first you should imagine system, right? Because every definition is with respect to the system. So the internal energy, the internal energy of a system is a system is the sum of the sum of various kinetic, sum of various kinetic and potential energy contributions. Potential energy contributions, right? So when you have considered any system, that system have some obviously some matter, whether it is solid, liquid or gas or some mixture. So that matter have some kinetic energy and potential energy, right? So it includes some of different kinetic and potential contribution which is present in the system. So we can say that E is equal to E kinetic, right? E kinetic. So kinetic means plus E potential, kinetic and potential, right? Now you can write here in the kinetic energy contribution, you can consider E translational, E translational plus E vibrational plus E rotational, right? Translational, rotational, vibrational, electronic, plus nuclear plus E positional plus E due to the mass contribution, right? So see, I have covered all these iron energies. So from here to here, this from here to here, this is the, this is the kinetic energy contribution, and this is the potential energy contribution, right? See, this positional includes the intermolecular, means molecule to molecule, intermolecular energy, bond energy, right? Bond energy, intermolecular energy, and binding energy. All these, types of energies which are associated with the molecule formation, that is included in this the positional. So I have taken a broader term here. So all these are the kinetic, and this is the potential, right? Potential energy. So I'm putting here a note, that is a very important note. Above 0 Kelvin, above 0 Kelvin means if T is greater than 0 Kelvin, all the energies listed here, all the energies which are which I have listed here, all contributes in the internal energy. Above 0 Kelvin, all above listed energies contributes in the internal energy. Internal energy, right? So this is the first point of important note. Now the second point is, at 0 Kelvin, at 0 Kelvin, that is T is equal to 0 Kelvin. See, translational motion ceased, rotational motion ceased, right? Rotational motion stopped, translational motion is stopped, vibrational motion is there, electronic kinetic energy is there, nuclear kinetic energy is there, and potential energy obviously is there, right? So at 0 Kelvin, except this translational and rotational, rest of the energies contributes in the internal. So this is very, very important concept. So see, at 0 Kelvin, what the energy will contribute in the internal energy? Vibrational kinetic energy, vibrational kinetic energy, electronic kinetic energy, electronic kinetic energy. This will also contributes in the internal energy. Nuclear kinetic energy. Nuclear kinetic energy, right? And positional positional potential energy. Different kinds of positional, different kind of positional potential energy, right? And energy as a result of having mass. And energy as a result of having mass, right? So at 0 Kelvin, all these energies will contribute in the total energy of the molecule. But theoretically, we say at what you can may have heard about that. Okay, at 0 Kelvin there is no energy to the system. This is not the truth. At 0 Kelvin, matter energy and matter will not disappear at 0 Kelvin. Matter is there, and if matter is there, definitely energy is there, right? At 0 Kelvin, only translational and rotational motions are ceased, right? So, we can say thermal energy. You see, thermal energy is a different issue. In thermal energy, the contribution of translational is there, vibrational is there, rotation. So, one should clear in his question whether he or she is talking about thermal energy or he or she is talking about what energy or internal energy. If you are talking about internal energy at 0 Kelvin, all these energies will contribute in the total energy. But in thermal energy, we consider the contribution of translational, rotational, and vibrational. Right? We are not considering I am correcting myself that translational, rotational, vibrational, and electronic. We are not considering the nuclear and positional and energy due to mass contribution. We are not considering all these energies in the thermal energy. Electronic energy is also very less. So there is a difference in internal energy and thermal internal energy. In thermodynamics, we are basically using this thermal energy, right? So thermal energy, if we are talking about the thermal energy, so in thermal energy, thermal internal energy, E thermal, this is equal to E translational plus E rotational plus E vibrational plus E electronic, right? So these are the contributions in thermal energy, right? This is equation 2 and this is equation 1 and a master equation. So I have tried here to clear the confusion between this internal energy and thermal energy, right? In thermal energy, these are contributing, and in internal energy, all the contributions must be included, right? So thermal energy, contributes in thermal energy. Translational motion contributes kinetic energy, rotational kinetic energy, vibrational kinetic energy, and electronic kinetic energy. Although the role of electronic kinetic energy is very small, vibrational kinetic energy contribution is also very small, and rotational and translational, they contribute significantly, right? So we can say that the contribution of electronic and vibrational energy is relatively small. Okay. So again, I am putting one note here, that the contribution of vibrational kinetic energy and electronic kinetic energy in the thermal energy thermal energy energy is relatively small, right? So we can write here E thermal is equal to E translational plus E rotational plus, I'm considering this vibrational also here, because vibrational have more contribution than this electronic, right? Plus uh, okay, vibrational. This is equation 3, because this electronic have even less contribution than vibrational. So basically in thermal energy, in future I will consider only these three, and although at room temperature I will not consider this, at higher temperature I can consider this, right? So this is the difference between internal energy and thermal energy, right? So be clear, at 0 Kelvin, all these are contributing in the total energy, but not the thermal energy, what we are talking about in this chapter. So in this chapter, whenever we are talking about energy, internal energy or thermal energy, so many times the meaning of that is thermal energy, thermal internal energy, right? So basically thermal internal energy, it depends on mainly these three, and at room temperature the contribution of vibration is also very less, right? So I will let you know what is the contribution of translational, rotational, and vibrational energy in the total energy, and accordingly we will develop the formula, right? Now, see, in the thermal energy, mainly translational, rotational, and vibrational. So, if you see E thermal, translational, right? This is equal to 1 by 2 RT per degree of freedom, per degree of freedom. So all of you are knowing that what is this degree of freedom? Degree of freedom, see the translational motion. So for any molecule can translate in how many ways? The number of ways through which a molecule can translate is called, that is known as that the translational degree of freedom, right? So any molecule can translate three ways, along x-axis, along y-axis, and along z-axis. So for any molecule, for any kind of molecule, whether it has one atom or more than one atom, maximum translational degree of freedom is equal to 3. Maximum and minimum, all total degree of freedom, translational degree of freedom 3. So in the coming lecture I will discuss about this degree of freedom. But what is the meaning of degree of freedom? Degree of freedom is the different ways a molecule can translate. That is called degree of freedom. Similarly, E thermal rotational. This is also equal to 1 by 2 RT per degree of freedom. Per degree of freedom, right? And E vibrational, little bit, this is complicated. E thermal vibrational is equal to RT into X by e to the power x minus 1. And this you can write is equivalent to RT. For simplicity, I am taking this because this term x by e to the power x minus 1, this is very small value, right? RT per degree of freedom. Per degree of freedom, right? And here x is equal to h nu by k into t, right? And if you put the value of this is Planck's constant, this is Boltzmann constant, this is temperature, so this becomes equal to 1.438 nu bar by t, right? So if you see this value t, if you put here, value of t, and here this wave number. So wave number, if you take in angstrom, so this will very small value, and if you divide with the temperature, again you will get so small value of x. So this is very small, e to the power x minus 1. So this term is we can ignore, and we can take RT, right? But don't say that this vibrational contribution is more than rotational, because here RT and here half RT, right? Because you know this term is multiplied by some constant, and that constant value has very small value at the given temperature. So at room temperature, the contribution of vibrational energy in the thermal energy is 0. We are taking this at room temperature. at room temperature the contribution of vibrational energy in thermal energy is negligible. Right? So basically at room temperature, mainly translational and rotational will contribute in the total energy of the molecule. Right? Clear to everybody? Good. So now see E thermal, what I have written. E thermal, we can define the E thermal is equal to energy of whole system at T Kelvin minus energy of system at 0 Kelvin. So this is our fundamental basic equation. So suppose that we have a system and we are defining the thermal energy for that system. What we define here in thermodynamics, we don't consider always the total energy. We always consider here in thermodynamics for thermal energy. So thermal energy at given temperature of that system minus energy at 0 Kelvin. See, I am not taking this at 0. I'm not taking this 0. So if you want to calculate the thermal energy, you can take total internal energy at this minus total internal energy of the system at 0 Kelvin. Now suppose that this is at T1 Kelvin. So this is E1. So E2 at some different temperature, E2 thermal is equal to ET2 minus E0 Kelvin. So at any moment of time, if you subtract this equation 1 from equation 2, so you can write delta E is equal to E2 minus E1 is equal to ET2 minus E at 0 Kelvin minus ET1 plus E at 0 Kelvin. So this is cancelled. So we will get ET2 minus ET1 delta E. So this is the reason we always prefer to evaluate or calculate change in internal energy, not the absolute value of internal energy for any system. Right? All of you are getting my point or not? So we always prefer to calculate the difference. So whatsoever the value, because if you take this value E at 0 Kelvin is 0, then you have the absolute value of internal energy, but it is not 0. As I have already discussed, I have told you that even at 0 Kelvin there is some energy present in the system, even some thermal energy is left in the system. That is called 0 point energy, unremovable part of kinetic energy from the system, right? So this is the reason why. So why we prefer to evaluate the difference? This is the reason, because this is the reference. The reference is energy of the system at 0 Kelvin. This is the reference. So if you have observed, then in every state function, thermodynamic function, I have written here change, enthalpy change, internal energy change, entropy change, right? So we always prefer to evaluate difference, not the absolute value, right? This is the reason. So now my calculation will proceed how to calculate this degree of freedom and total energy of different kinds of gas molecules, right? So this is the explanation why we are preferring to evaluate difference of energy, not the absolute value. We cannot say that we cannot determine the absolute value. We can determine the absolute value, but this value is with some error, right? And the error is equal to the energy left in the system at 0 Kelvin, right? So to avoid that error, we always prefer, to evaluate the difference. So we always prefer to evaluate the difference of energy or internal energy. Internal energy, not absolute value. Absolute value, right? So this is the theoretical concept basically to determine the difference, not the absolute value. If you want, you can determine the absolute value as well, no problem. Okay, so this is introduction about the internal energy. What is the meaning of internal energy? What different energies are contributing in the internal energy? Above 0 Kelvin, what is the contribution of different energies, and at 0 Kelvin, what the different components contributing in the internal energy of the system? What is thermal energy, and what different contributions are in the thermal energy? What contribution is more and which contribute is less? Everything I have clearly mentioned here. And here I have left one question: how to calculate degree of freedom and total energy. So in the next class, I will discuss about that, right?